Oh, I'm not sure because and then
Yeah,
I tried
it'll be
to
good.
finish it, but I didn't, so I
It'll
didn't
be
finish it.
okay. Albert is saying he's in the same boat as for 16.1. David is saying he has number 1. Oh,
I try like 16.4, but
yeah. Yeah, why don't you show it? You show it, and David,
I
you show.
show whatever I did, but and then it's the final answer. I know the final answer, but I didn't complete it. But I don't have time, so I just work on it. So that's good.
Yeah, let's see it.
Okay.
Maybe Albert and David. Let's see. You know, one of you can show 15. Maybe the first one. Because it's good for 16 to do some presentations
Yeah, I
for 16.
know. So
A
yeah,
lot of technical,
a lot of work. So that's why I cannot
a lot of
finish complete.
correct.
Yeah.
Okay, let's do it.
Okay.
So I
Sure.
made you a presenter
I try
ready.
my
Let me
best.
do.
Okay. So
Yeah,
all
that's
right.
good enough for life. You know, in life, all we can do is try our best.
Okay. Sure. Okay. Thanks.
Then David, you can prepare yourself for showing question 1. If anyone else like to show your work or present, just let me know. We're just waiting for Shuxian to be ready to show 16.4. Shuxian, what's up with you? Can't hear you. Okay, David, are you ready to show yours?
I'm currently trying to upload it right now because I wasn't ready. It'll take like 1 minute. I'm almost there.
Yeah.
It's there you
Yeah.
go.
Shuxian's up, right? That's Shuxian's.
That's
Or
my.
that's yours.
That's mine. That's
Oh,
mine.
okay. Yeah.
I try my best to explain, but if okay, okay. Today I try to present the 16.4 find all possible Frobenius solution. If the Frobenius solution does not exist, show why it doesn't. Okay, I choose and then the question 4. That's like a equation like a s sum y double prime plus 4 minus x like sum first double prime minus y equals 0. So first of all, I like both sides. I write over there dy like x. So make the equation become like y double prime plus like this and capital Qy like turn sum like a y pi minus 1 over xy equals 0 because we have like no that is form for this. So that's why we can find the small p of x equal 4 minus x. And then here over here I circle that x is like a small like q of x is negative x because the from over here I wrote here underline this from this is a plus, so that's like q of x is negative. So I found out I plug in if like a x like a p of p naught is 4 because this 0 is x is 0 is p of 0 is 4 and Q of 0 is 0. Oh, no, yeah, correct. So now I plug in into the integral equation over here. That equation is R times and then the R minus 1 plus P naught times R plus Q naught equals 0. So I plug in, get this is like a equation. I like calculate there. I get the solution is R1 is 0. R2 is -3. Maybe it's not clear over there, but it's if you figure out that induction equation, you can find out like a root is R1 and R2. And is R1 minus R2 equal like 3 is a positive integer. So that's why here this equation have two solutions. So and then I let this y equal this power series equation. Y double pi is no, y pi is for this one, y double pi for this power series equation. So as we know, so I plug in for this one's x, the equation we have. So I need to figure out the index. So the final term is 2. A lot of word get over there. The final is like a power series is n equals 0. Here, the coefficient is n plus r, the power 2 plus 3 n plus 1, like times cn times xn. The power is n plus r minus 1. In here too, but here is n equal 1 is to the infinity is in coefficient is n plus r is c n minus 1 x n plus r minus 1 because and then we know how to do the index because here the x in the first one over here is x is n plus r plus r minus 1 is not can factor from x power n plus r, we suppose, and make the x power like the same. So we can work and then the follow. So the term corresponding to n is to this integral equation. So if we let the n equals 0, I plug in, but I didn't write down because here these two like power series, and then they have the x power is same, and then we can and then the plugs all they are coefficient together. This is minor. I did like here because here the n equals 0, so I only take the 0 power series is n plus r, like a power 2 plus 3 n plus r is like a get the term if since like r times like r plus 3 equals 0 for both rule mean it's r1 and r2 and c naught because n is 0 is cn is c naught is for all the constant. So that's why we can not make the pattern for this n one term. So here have n equal 1, so we make the n suppose a grade and equal 1. Here, suppose have 2 together. So I make this equation equals 0. And then I calculate all, and then, so I get this one. So we have like a relation between Cn and Cn minus 1 and equals 0. So but you know for in here, if here have like a figure out over here n minus 3 times n times cn minus r minus 3 cn minus 1 equals 0. So n cannot be 3. If be 3 like a 0. So that's why here the n cannot be 3. So we have like a figure out the Cn equal like a Cn minus 1 over n, because I calculate this equation. We have over here the n cannot be 3, so that's why we can calculate if n equal 1, C1 equals C0. If like n equal 2, C2 equal 1 over 2 C0. If n equal 3, C3 is like a 1 over 6 C0. So if n if like n equal 3, this one cannot be, because C1 and C3 here, we have to calculate the 0 times like a C3 over 0 times like C2 equal 0. But we know like a C1 and C0 is not be 0. So if like n greater than 3, so if n equal 4, we have this one. So n equal 5, C5 is like this term, but C6 like over here. But we figure out if like we have the C just up to here. Just up to here, Professor.
Oh, okay.
I think if like Cn suppose like equal like 6 C3 over like 5 factorial. So that's why I figure out like a Cn, no, C2n plus 1 over here. So I confuse it too. So
No,
that's
it's
why.
okay. It's okay.
I
So
try to
because
figure out, because and then the two solution is y 1 over x is like n equals 0, n equal 1, n equal 2, n equal 3, plus together is like a y1, y over 1, and then y2 is like a n equal 4 and up. That's like a solution y1 and y2, I guess.
okay, so you're almost done actually. Because your
Yeah.
case, your case is R1 and R3 differ by an integer. So differ by an integer, you have two solutions. So y1, if you writing for -3, so that's for -3 solution, you have C0. Then you have, let me see what else you have.
R1 is 0.
Huh?
R1 is 0 means it's like all the like
But
y
this
of
solution,
R1 is, yeah.
so your y1 is for, because you are written, you started with the x raised by -3. So I
Yeah.
assume this is for R2 because your R2 is -3. Right. So you just keep writing because you have the relation already. You have a Cn equals to Cn minus 1 over n of Cn minus 1, right?
Yeah.
You just have to write a summation sign. Right, you have your first term, then you have your summation sign, then your n start with 1.
Yeah.
Your n start with 1 to infinity, then you have this relation Cn equals Cn minus 1 divided by n, x raised by n, right?
Yeah, I got it. Yeah.
Yeah, then you
And
have
then
y2,
finish.
right? y2 just differ by, because your two integers differ by an integer, so your y2 is a k, is some constant.
Yeah, just like I said, like Cn, C1 and C2 like constants.
Right, you know how to do it, right? You just didn't have enough time to finish.
I cannot finish, so I don't have time to finish, so I just want to show
You know
so that's good.
So you know how to finish. So you know
Yeah.
you almost finished. 2 lines you finished.
Yeah.
Okay.
Yeah.
Anyone
almost.
has any questions, right? So this is tedious working, but you know, we need to know how to do it. So anyone has any question? Okay, great. Thank you, Sushan.
Thank you. Thanks.
Thank you. Okay, David.
Okay, so the question is to define all possible Frobenius solutions, and if it doesn't exist, show why it does not exist. And so our equation is x squared y double prime plus x y prime plus x squared minus 4y equals 0. And so we do the usual thing, right? We have to find our p naught and q naught. We divide under. Our p is x over x squared, or q is x squared minus 4 over x squared. And then you do the usual procedure. You multiply the big P of x by an x. That gives you small p of x. Q of x, same thing. And then you just assess at 0. P naught is 1. Q naught is negative 4. And then you can plug this into your indicial equation. I have the P naught in front of the R, and then I have the Q naught standing by itself. It simplifies nicely into R squared minus 4. You can factor and you get R equals 2 and R2 equals negative 2. And I think from the notes, R1 is supposed to be the larger one and R2 is the smaller one. That seems to be what they're doing.
Yeah, in reality, we don't really care, but anyway.
Okay, yeah.
Yeah.
All right, and then so next I plug in my series for Frobenius solutions of equivalence to y double prime, y prime, and y. And so there's the new equation. And then I insert my x's into my summations, and I adjust the exponential. So for x squared, the x to the n plus r minus 2 just becomes x to the n plus r. Same thing happens with the y prime. It just turns to x to the n plus r. It works out really nicely. And then I apply the x squared to the y, and then the minus 4 to the y again, because it factors. And then after that, I basically just adjust, because I'm trying to get the same exponential, right? I adjust my index to start at n equals 2 for this x squared going into the c of n x to the n plus r, which is just the y, right? And then I put all my x to the n plus r's together. I do some math. It works out not bad. I end up with, here at the end, I end up with n squared plus r squared plus 2nr minus 4. And that's inside of the brackets of my c of n. I forgot to put the x to the n plus r over there. So that's something. And then, of course, this drags along. N equals 2 c of n minus 2 x to the n plus r. And so what we're supposed to do here is we're supposed to let n equal 0. This is what I found in the notes. And you do this so that you can assess your c of naught. This is important because it will help you see what is in the future for your solution. And so over here, I plug in n equals 0, and I get r squared minus 4 c of naught equals 0. Now this means that c of naught can be any number. This is because if r equals either of its solutions, right, then that means the inside of that, inside the brackets will be 0, which means that c of naught doesn't necessarily have to be 0. It can be any number. So that's good in terms of getting a solution, I believe. And then we check at n equals 1. I believe this is because our index over here on the right goes from n equals 2 to infinity. I'm not sure if this is correct, but that seems to be the
You're
reasoning
correct.
when
You
I
have
look
to
in the notes.
consider, right, because you start with 2, you have to consider n equals 0, n equals 1 separately.
Yeah, okay, that's good to know. I thought it might be that, but I wasn't 100% sure. And so we check n equals 1, and we get this thing. I wrote a bracket around it, and then c of 1 equals 0. And so when we check our r's, what does it say? Anyways, when we check our r's, wrong r's. I don't know why I put in -1, 3. When we put in 2, yeah, it still works. We will be getting a value in the brackets, which means that C of 1 must be 0, right? Because if we multiply some non-zero number by something else, it can't be anything, you know. It can't equal 0. C1 must be 0. And so after that, we can use our general equation because we're past, well, we're at 2 and past that. So here's the equation, n squared plus r squared plus 2nr minus 4 times c of n plus c of n minus 2 equals 0. And then we can check at r equals -2, the smaller of our r's, plug it in. We end up getting n squared minus 4n plus the times c of n plus 2, c of n minus 2 equals 0. Rearrange the equation, get a recursion relation, c of n equals c of n minus 2 over n times n minus 4. And then obviously we can't have n equal 4. That's not allowed. Obviously, you know, yeah, and you could also verify this by saying if n equals 4, you go back and look at that original equation. That would just mean that like c of naught equals 0, and this was not the case beforehand. And if there's, I wrote here, if there's no way to choose c of 0 to satisfy the equation, so there's no Frobenius series solution for r equals -2. I think that is the correct reasoning. And so that means I got to check the other one, right? So r equals 2, same thing, recursion relation, a little bit different. Denominator is n plus 4, so we're good with the positive values of n. We won't be getting a 0 in the denominator. And then so basically I let n equal 1 here. Why did I do this? Well, anyways, it turns out that all odd c of n's are 0. Oh, yeah, this is why. 5c of 1 equals 0, and therefore c of 1 equals 0, and so everything after that will just be 0 when you do that relation, since there's a difference of 2. N equals 2, I plug it in. N equals 4, I plug that in. I end up getting this relation. I think this is correct. Anyways, yeah, that, and then you could put it into the general formula, c naught times x to the second power, because r is 2 in this case, and then 1 plus the sum of n equals 1, I believe, to infinity times that recursion relation until it goes on forever. And so y of 1 is the solution to our original formula, and y2 is a solution we could get, but is not a Frobenius solution, so I didn't pursue that any further.
Right. That's great. That's great. That's very nice. Thank you, David. Oh, Albert is saying he's not close enough to the solution. But a good try and keep trying. Yeah, sure, Albert. Present next time. I think Moses wants to present. You mean 17.2, right? Go ahead.
Yeah, something.
Yeah, 17.2.
Can you see it?
Yeah.
Okay. So for this question, it asks us to show that, well, to prove that gamma of x plus 5 equals to this over here, x plus 4 times x plus 3 times x plus 2 times x plus 1 times x, and times gamma of x. And so we know from the notes that, well, gamma of x is just an equation. It's just an integral from 0 to infinity of e to the negative t times t to the x minus 1 dt, where x has to be positive. And also we know from that same equation that gamma of x plus 1 is equal to x times gamma of x. So knowing that, we can pretty much just rearrange the original equation, gamma of x plus 5, into forms that we into forms of x plus 1, let's say. So in here in the first line, I made gamma of x plus 5 equal to gamma of parentheses x plus 4 plus 1, and I made the x plus 4 my x,
Nice.
quote unquote.
Yeah, good.
And so that made me able to put it as my result for that to x plus 4 gamma of x plus 4. And so I pretty much just did that over and over until I had the final gamma of x plus 1, which we know from the original rule that gamma of x plus 1 equals to x gamma of x, which just proves that it is true.
Okay, nice. So this is a good question to present because this could be the starting point of my 17 notes. So this is a gamma function. Gamma function actually is gamma of x plus 6 equals to x, oh, this is x plus 5.
X plus 5, yeah, sorry.
Yeah, you could understand, you could think as x plus 4 factorial. Okay, you see this is a factorial?
Yeah, I just wanted to show it like more
Very
steps.
nice. Yes, very good. Okay, let's study gamma function as a solution of differential equations. Gamma function is a very interesting function. If you major in mathematics, if you plan to do your PhD in number theory, you deal with gamma functions all the time. Okay, so the gamma function and Bessel functions. Bessel equation of order p greater than or equal to 0 is of this case, right? Remember, just x squared be the coefficient of y prime, x be the coefficient of y prime, y double prime, x squared for the y double prime, x for y prime, x squared minus p squared, p is some non-negative number. The coefficient for y, then this equals 0. So differential equations like this, solutions are called Bessel functions of order p. Right, we rewrite it as a PQ form. Then lowercase p is x times capital P, which is give us 1. So evaluate p naught, which is 1. Little case q is x squared times capital Q, which is just x squared minus p squared. And q naught is just negative p squared. So initial equation, we have r times r minus 1. Remember, this is p naught, the coefficient of r is p naught. P naught is 1, so this is 1r. Then plus a q naught, or q naught just negative p squared. Right, so we get this initial equation. We simplify, we get this. Then we get two solutions. R equals plus minus p. Okay, so this is solutions as Bessel's functions of order p. So we have the initial equation solution to be positive, negative, p. P itself is non-negative. So we substitute y with some coefficient and of x raised to m plus r, and m start with 0 into this. So x squared times y double prime, x times y prime, and x squared minus p squared times y. We simplify, we simplify, we simplify, we simplify. Then we see this is starting from 0, but this starts from 2, so we have to deal with 0 and 2, m equals 0, m equals 2 separately. So if m is 0, we plug in, we get this. R squared minus p squared, C naught equals 0. So since R squared minus p squared equals 0 for the two solutions, for R equals plus minus p. So that means the C naught can be any number. For m equals to 1, we plug back in, we get this, and we simplify. In the end, we say, okay, if r equals -½ we get some C1. If otherwise, C1 is 0. So only for one value of r equals to -½ C1 is not 0. Then the rest of it, starting from 2, we get a recursive relation. So the m's term and m's minus 1 term minus 2 term with this relation. So for case r equals p, positive p, then remember r is positive p and negative p, two solutions. For r equals p, we plug back in. And we plug back in using AM for CM, just notations, okay? Because when we solve for p, we just want to use another variable for the coefficient. So you don't really have to use another variable to change it if you have a clear mind. Even it's the same variable, but a variable is a variable. A variable is just a representative. It could be Emmy, could be Tony. If you head can think, k equals k plus 2, stuff like that, you don't have to do this change, use AM for CM, stuff like that. So in this case, we get, this relation carries from this. Why we use AM? Because now we're solving for P. So later on, we're going to solve for negative P, right? So negative P, maybe we use BM, so we don't get confused. But if you know yourself not going to be confused, you can, keep it as a CM. So because A1 is 0, so all the R term is 0, right? Because the two terms either all odd or all even. So for the odd terms depends on A1. A1 is 0, so all the odd terms are 0. For the even terms, we can evaluate m equals to 2, get such with A naught. M equals to 4, we get such with A naught. So can 6, doing this is just help us to find a pattern. Okay, find a pattern, so can form the nth term or 2nth term, 2m's term. So we observe the pattern, we see, okay, A to M and A naught have the relation with this scalar. This scalar. And to write in the pattern, so that's -1, so alternate, terms, so 2 to the m, because we have 2 times 4 times 6 times 2 to the m. So each one we can factor out 2. And how many we have? We have 2m of them, so 2 to the 2m. Then once we factor out, we have 1 times 2 times 3 up to m, so that's m factorial. Oh, here we have m of 2's, right? And here we have another m of 2's because we factor out 2 from these two. After we factor out 2, we have p plus 1, p plus 2, up to p plus m. So we have a p plus 1, p plus 2, p plus m. So then we have a solution. So the solution for r equals p, we have this a naught, x raised by p. X raised by p sometimes we write up front, x raised by p, a naught, x raised by p. Sometimes we write in the exponent, which is combined with the exponent of x to m. So x raised by 2m plus p. Then with the recursive relation. Anyone has any question? Very similar to before, right? What's different? The different is R equals to plus minus P. Before we have R to be two different numbers. Either, they could be differed by fraction, could differ by an integer. Now, the integral equation has two solutions that are additive inverse. So we get one solution as such. So let's see, this is saying P, if P can be 0, right? Because P is non-negative, that means P can be 0. So if P is 0, so that's only one forbidden series solution, because plus minus 0, both zeros, both 0. So second case, when R equals negative P, remember we restrict the P to be non-negative, so negative P is less than or equal to 0, but we have dealt with 0 case, so negative P is negative number. So plug back in, so this is simplified to be this. Now we use BM, for the solution negative P. So we rewrite CM into this case. So B naught can be any constant, and the B1 is 0, right, if we plug in, unless just for one number. So this is, if P is either a positive integer or an odd multiple, greater than or equal to 3, multiple of negative half, then m minus 2p, right, m minus 2p, will equal 0 for some positive integer m. If that happens, there will be no solution for this, right? If the m minus 2 term is not 0. If p equals to some k is some odd positive integer. Because if k is even, this p is an integer. So if k is some odd integer, so forces p to be a fraction. So what happens? Then we don't have a problem because we can choose b m equals 0 for all odd m. So if p is not positive integer, we have such a relation, right, for m starts from 2. Then we get y2 of x, so this is for negative p, right? So the solution for negative p. So we have negative, so the previous one, all the positive p's, now it's just changed to be negative p. So they become 2m minus p. We still have 2 raised by 2m and m factorial, but this becomes negative p plus 1 or 1 minus p, 2 minus p, m up to m minus p. We'll have to deal with this case separately. So if r is a negative half, then b1 is some number. And the second solution regarding r equals to negative p, so we have something like this, x raised by negative half cosine x plus b1 x raised by negative half sine x. According to our previous knowledge we have done previously. So if r equals to positive half, y1 will be, we'll use different notation, a naught x raised by negative half sine x. So we can take a b1 equals 0. b1 equals 0, right? So in this case, we have this. Okay, anyone has any questions? Just a lot of calculations. Because the solution is plus minus p, So we have to consider, some different cases. P as integer or P as a fraction. P as a fraction. So the power series representation for y1 and y2 converges for positive numbers of x, since x equals 0 is the only singular point of the differential equation. Okay, now our focus to the gamma function. All right, Moses already started the gamma function. Let's see the definition. The definition is this. So this is capital gamma. Gamma of x equals to this integral from 0 to infinity, e to the negative t, t to the x minus 1 dt. Okay, so we can see dt is a dummy variable here because the gamma function is x is a variable. So in terms of x, because this from 0, the integral is from 0 to infinity. So we have another variable appear here, t. So this is defined for positive value of x, right? So t raised by, so x is positive. So I have two parts. The first part is gamma 1 equals to 1. Gamma 1 equals 1, because for x equals 1, right? So t raised by 0 becomes 1. So we only have e to the negative t dt. How do we deal with this? When the infinity sign in the upper limit or lower limit, we take a limit, right? We take a limit, we let the dummy variable run into infinity. That's how we deal with this. Either upper limit or lower limit involves infinity sign. So gamma 1 equals 1. And gamma of x plus 1 equals the x times gamma of x. So Moses proved gamma of x plus 5 equals to x plus 4 times x plus 3 times x plus 2 times x plus 1 times gamma x. Right? Gamma x was gamma x. You could think gamma x can be x minus 1 times gamma of x minus 2, so on and so forth, until gamma of 1. And the gamma of 1, which is 1. So in general, we think gamma of x plus 1 equals to x factorial. So this little proof here, gamma of x plus 1, let's take a limit of this, so integrate by parts. Yeah, it won't be difficult, right? You may go through this to see that equals to x gamma of x. So give some numbers. Gamma of 2, there's 1 times gamma of 1. Gamma of 1 is 1, so that's 1 factorial. Gamma of 3, that's 2 times gamma of 2. What's gamma of 2? Gamma of 2 is 1 factorial, so that's 2 factorial. What's gamma 4? 3 times gamma 3. What's gamma 3? 2 factorial. 3 times 2 factorial, that's 3 factorial, so on and so forth. So in general, gamma of n plus 1 equals to n factorial. Right? So n is a non-negative integer. Anyone has any question? Okay, a special value of gamma function is this. Oh, so the domain of gamma can be half, can be negative half. Gamma just don't take negative integers. Okay, let's like a -1, -2, -4. Negative numbers, negative integers not in the domain of gamma. Then all other functions in the domain of gamma. Even complex numbers. So gamma of half, right? If we plug in x into half, then we try to do that, then we see gamma half equals the square root of pi. So this is a famous guy. So gamma half equals the square root of pi. The gamma function is defined for positive integers of x. However, we can extend its definition to negative x such that x is not a negative integer. It could be negative half. We can do this through the relationship of such. So gamma of x plus 1 equals x times gamma of x. Then gamma of x, we divide by x on both sides. Gamma of x equals gamma of x plus 1 divided by x. So for example, if x plus 1 is positive, then gamma of x plus 1 is defined. We can then define gamma of x equals to gamma of x plus 1 divided by x for the interval from -1 to 0. Now the gamma of x is defined for in the interval from -1 to 0. We can define gamma of x, keep going from -1 to -2. This is still okay, continuing the process. So we get a definition of gamma for all negative numbers except negative integers. So the graph of gamma is very interesting as well. You see the negative integers not in the domain of the function. Okay, Bessel functions of the first kind. So the solution, okay, anyone has any question actually? All right, Bessel function of the first kind. The solution to this equation corresponding to r equals to positive p is we have seen earlier, right? So if we choose a naught equals 1 over 2 raised by p is some positive number, gamma of p plus 1. And use this gamma of p plus m plus 1, well, what's that? That's p plus m factorial, right? Well, can be written as p plus m times p plus m minus 1, until p plus 1, then gamma of p plus 1, right? Just like a 3 factorial can be written as 3 times 2 factorial, so on and so forth. So which follows from gamma of x plus 1 equals x gamma of x. So we get the first solution to be, we just rewrite in that case. So this becomes gamma of p plus 1 times p plus 1, until p plus m, right? But here we still have 2 to the 2m, 2 to the p, m factorial. Let's see, we simplify this a little bit. So 2 to the 2m plus p, 2 to the 2m plus p, m factorial, or gamma of m plus p plus 1, right? Because this is gamma of p plus 1 times p plus 1, until p plus m. That is gamma of m plus p plus 1. So if we write, because we see this is 2 raised by 2m plus p, this is x raised by 2m plus p. So they have the same exponent. We can write this together as x divided by 2, then raised by 2m plus p. So in this case, we see this coefficient is very neat. With -1 raised by m factorial, gamma of m plus p plus 1. Anyone has any question? So this is called the Bessel function of a first kind of order p. Right? We use this J with full node p to represent the first kind of order p for Bessel's function. So just this, m from 0, the summation sign to infinity, and -1 raised by m factor divided by m factorial, gamma of m plus p plus 1, then x divided by 2 raised by 2m plus p. So similarly, if p positive is not an integer, right? It could be a fraction. And we choose b naught to be 1 over 2 raised by negative p and gamma of 1 minus p, right? That's for the second case. Remember, when p is negative, we have for this case. So we choose b naught to be 2 raised by negative p and gamma of 1 minus p. In the Frobenius solution corresponding to r equals negative p. And if we do this, what do we get? So we have b naught multiplied by this, just as similarly as a naught multiplied by the mth term. So combine, we simplify. So in the end, we get -1 raised by m factorial, but a gamma of 1 minus p plus m. Right? And the same thing for this x divided by 2 raised by 2m minus p, right? Before the 2m plus p. We see just, the p, positive p become a negative p. So we noted with J with a full node negative p of x, right? So in general, we have the solution as some constant, right? P, first kind of p order, and some constant, and the first kind of negative p order. So we have this linear combination as a general solution for positive x. For positive x. X can be fraction, x can be integer. To get an answer for negative x, so we need to replace x raised by p with absolute value of x raised by p. So in the two cases, right? So if p equals n, a non-negative integer, then we use the n. So n usually represents a natural number, counting number. So this is the first kind of nth order of Bessel's. So we just have change p to be n plus m plus 1. This is 2m plus n. Right? And if n is just a natural number, so we know this is n plus m factorial for gamma of n plus m plus 1. So for zero order, right? For zero order, we just get this. For first order, we plug in, get some terms like that. So the graph of 0 order and the first order, just like this. Anyone has any question? Looks a little bit like before when we were talking about the damped, right? Anyway, so similar to the solutions between cosine and sine. So we have this relation. So the first derivative of 0 order of bezels, first kind of bezels, equals to negative first order of first kind of bezel. Second kind. So if p is an integer, n, then the solution to this bezel equation has y1 as a solution. There is no second Frobenius series, so the general solution will be some constant with nth order bezel, first kind, plus some constant, this yn of x. So what is this yn of x? So this yn of x is 2 over pi, this lowercase gamma, plus ln of x divided by 2 times this nth order bezel minus 1 over pi. Then m goes from 0, summation sign for m goes from 0 up to n minus 1 with this if you actually this can be written together 2 raised by n minus 2m, x raised by n minus 2m can be written together. We'll make this neater. Then minus the rest of the goes from 0 to infinity. Have this. And now we see another letter hm, hm plus m plus n. Okay. So what is this gamma? What is this h? So gamma is the limit of n approaching infinity. This summation goes from 1 to n, 1 over k minus ln n. And this is called Euler's constant. Gamma, lowercase gamma. Gamma function is capital case gamma. And what's hm? hm is defined as a summation of from 1 to m of 1 over k. Right? So 1 plus a half plus 1/3 until 1 over m. So this yn is called the Bessel function of the second kind of nth order. Okay, anyone has any questions? Okay, Bessel function relationships. So we have this fourth type of order P, right? So if P is a non-negative integer, then we can take a derivative on both sides. So this is saying, okay, let's multiply x raised by p on the left-hand side. Let's multiply x raised by p on the right-hand side. So we have this. So that's why this 2m plus p now becomes x raised by 2m plus 2p. So we have this x to the p. So differentiate this. So in the end, simplify. So we show that's x raised by p p minus 1, the order of p minus 1. Right? So differentiate this to get this. So we have this differential of this, we get this. So similarly, if p is negative, negative, we get this is negative x raised by negative p of this. So differentiate this and differentiate this. So what do we get? You know, can simplify, get to the derivative of the bezels. The derivative of bezels, we see all that equals to those two terms. So subtracting those equations, we get, when we get this, subtract those two, get 0. Then the other side, get something like this. This is a recurrence relation, right? Because we see p minus 1, p, and the p plus 1. So recurrence relationship between Bessel functions of first kind. Right? P minus 1, P multiplied by something, the P plus 1. So those three terms adds up to be 0. Let's see an example. So when P equals 1, right, we differentiate this. Right? Using this, so what do we get? X raised by 1, because x raised by p, just x raised by 1. X raised by p, just x raised by 1. Then integrate both sides. Integrate both sides. So get this side plus some constant equals this. What does this tell us? So this is just seeing the first order, right? First order of bezels multiplied by x with some constant. Well, this constant we can put on either side equals to this integration of this. So this is the first type of 0 order. This is the first order. So we just have this, kind of neat relation. Let's see, this, if p equals 0, what do we get? We get x raised by 0, which is just 1. So this becomes a negative 1. So we just have this, right? Integrating, so we have the 0 order equals to this negative term, or plus or minus some constant. So let's see this one. This one is saying find this one. So this is in the integrand, this is x squared. In the integrand, this is x cubed. So find this and this in terms of Bessel functions. And without this and this, without x squared or x cubed in the integrand. So we integrate by parts, right? Use the previous example. Integration of this by using the relationship. So this is for negative. Right? p is positive, x squared, x raised by 3 is positive. So that's just x squared j1x minus this integration x j1 of x dx. So integrating by parts, so in the end, what do we get? We get this one, the first one, this one, with x squared inside the integrand. That equals to x squared j1x times x j0 of x minus integral of j0 of x dx. For x cubed in the integrand, we get x cubed j1 minus this integration of 2x squared j1 of x dx. Same thing. In the end, after the calculation, we get x cubed j1 of x plus 2x squared j0x j0 of x minus 4x j1 of x plus some constant number. Any questions? So Bessel's functions, gamma functions are very interesting functions. We have these recursive relationships among their terms. Okay, that's all I have to talk about today. So basically gamma functions and Bessel functions, I think we have a little bit of sense of those two kinds of functions now. Bessel function we have first kind, second kind. Gamma function was invented, for writing some terms neatly. Anyway, anyone has any questions? Yes, David.
The derivative of the Bessel function, is that just like defined as like, is that just the general rule where you just...
You mean this?
Yeah. Is there a derivation?
What do you mean?
Oh, I see it. Page 10. Never mind. It's okay.
Oh, okay. Okay, anyone has any other questions? Right. So this is a tedious calculation. I didn't really go through it, and yeah, go through yourself to convince yourself such relation, such relation. Okay, take a derivative of xp, jp, and you get this. So you see the order p and the order p minus 1 has a recursion relationships with its derivative. Okay, if you have no question, you're a free bird, go ahead, try your homework. If you do have questions, I'm still here talking to you. I'm going to stop recording.